Hello, everybody, and welcome to this session about explainable machine learning, or at least explainable machine learning explained. Now, my name's Peter Dorrington, and I'm the Chief Strategy Officer at Anthralytics. But more importantly, I'm the host for this session, and I'm delighted to be joined today by Karol, who's the CTO at Codet and MedTransfer. Now, Karol has been working with Fortune 500 companies on data science projects for years. He's also built a research lab for machine learning methods and big data solutions at Codet. So in this session, Karol's going to be talking about explainable AI, a hot topic today. And we've seen a boom in AI because deep learning methods have made such a huge difference in many scenarios and use cases. So during his talk, Karol will also explain some of the explainable AI methods and going to use a focus on medtech and fintech. So without further ado, I'm going to hand over to Karol. I'm going to disappear off screen. Let's get the right one. And I'll be back in a few minutes to talk with questions. But Karol, over to you.
Thank you, Peter, for the introduction, and thank you everyone for joining me today. I hope you can see my presentation. So what I do, I do machine learning for about 15 years now, mostly in the medical field. You can find some of my research papers on Google Scholar, for example. That's why I focus also on explainability, because in the medical field it is crucial not to develop machine learning models, because this is something that you can do without explainability. But if you want to commercialize that, then definitely that's something that you need to use just to get an FDA approval. So if you're interested in actually finding more about what I did scientifical, then please find me on Google Scholar. If you want to learn more about some other topics related to machine learning, you can also find me on YouTube. So my experience came from not just from the scientific, let's say from the university, but also from the company that I raised and I founded 12 years ago, and that we are now around 400 people doing different kind of projects. Just to mention a few here. That we helping to grow, and some of them are actually the products are based on machine learning models. So just to give you a short introduction, so the presentation isn't really, I hope it's not so difficult to understand. I tried to make it simple for everyone, for beginners. So AI, as you see in the recent years, it became a buzzword. And I do machine learning for 15 years, as I said, but currently we see a huge growth in the numbers when it comes to applications of machine learning. And there are plenty of use cases, like just the medical part that I'm focused mostly on, but we see also different ones where actually it makes sense. It is not just a buzzword, like like many others, like blockchain, I don't know, data science, and so on. You might see many more applications, useful applications. Even you use on daily basis some models like with your mobile phone, for example, right? You have Siri or such other similar solutions where actually the machine learning works under the hood. So that's good. Hopefully it will not change so fast. But anyway, you have the hype curve that is makes the let's say that the terms related to machine learning, but not only, but any kind of buzzword, makes them more mature in the, let's say, later stage, let's say. So explainability, it's more about understanding how the models works. So what's going on under the hood? Why do we get this kind of a decision? We also can you can also find two other terms, like interpretable artificial intelligence or responsible artificial intelligence, as two terms that are, it's not exactly the same, but because there are some details that makes the terms different terms. But you can actually, if you say that actually explainable AI, interpretable AI, and responsible AI is the same, then you are not far from the from the true, because in many cases they are used to actually mean the same. So if you look for any kind of publications, you can find that three of these the terms used. So why we actually use explainability? Well, first of all, because I mentioned already the FDA, to get an FDA approval if you have a medical application, right? It includes the device or just a model that is used for any kind of analysis. So you also want to explain, the domain experts, right? The one that actually understand the business, but might not really understand the machine learning, how it works. So it's good for them to understand why we take test solution, and it applies to any kind of industry. So for sure, such type of experts are the managers, right, or the executive board members that might be also interested why we have this model, why it works like that, or why it doesn't work. Right, because sometimes we do invest a lot of money, effort to actually build something, and at the end it doesn't work for some reason. And that's something that might be also very useful to explain that. For debugging, the data scientists, right, they are also interested how it works in the back. They are obviously, they are involved in that. So they might not be surprised, let's say, how it works under the hood, but they also want to understand why this type of weights or this type of layer set this kind of weight, and why is it actually why does it influence the other ones, for example. And at the end, we have also the users that are actually affected by the models. You can imagine, the credit score method. If you use a machine learning model, they want to know why, not just because our weight changed in our neural network, but they want to specifically know why they get a credit or not, for example. Right? So there are different types of explanations. So we have the text explanation. So we explain, well, this is more popular, let's say, in the scientific world. If you have some research papers, it's usually with some text explained, some equations, right? So we explain what's going on in well, not always in a way that is understandable by anyone. It's more for the people actually who are more into the topic, let's say. But this is also a way of explainable, of explaining the model. The second type is actually the visual one, and that's the most popular one. Why? Because people like images, like plots, and it's easier to understand how it works using an image. You can also explain it locally. So instead of actually explaining the whole model, just to take a part of it, right? Or take an example, right? Okay, this is the input. Let's go through like that, and at the end you have a specific result. Taking a specific example that is easy to understand, or simplify a very complex neural network. So we actually deep neural networks are these days very popular, and simplifying not the network itself, but actually explaining the part of the network might be also a way how to do that. You have also the feature relevance explanation. So if you have some features, like let's say if you have an image of a dog, so the features might be, I don't know, the nose, the ears. So explaining how the features are actually affecting the final result. Right. All right. So here have an example of skin cancer. So this is actually a topic that I'm involved, that I do and analyze for, I don't know, 12 years now, or even longer. And well, I already know, just looking at the pictures, where you have a cancer, which one is actually is a cancer and which one is not. But you want to know, as a medical doctor, as a dermatologist, you also might know which one is one. But if you go into the details, like multispectral images or something like that, something more complex, then you want to explain why the method that you have built thinks that this is a cancer or not. Or here, an example, right? Um, there is a well-known case with the husky and wolf dogs. with the husky dogs and wolves. Some researchers made a paper, made a model to distinguish between these two. If you know how a husky dog looks like, it's similar. I mean, for normal people, let's say, it looks very similar to a wolf. So what the researchers did, they actually feed it the model with some images, and at the end they actually obtained 90% accuracy, around 90%. So it's quite high. But then they actually try to explain what actually are the features on the image that make it would make the accuracy such high. And they figure out, you can see here on the right image, that actually the gray part is are the pixels, or the part of image that doesn't has any influence to the final decision. And as you can see here, in this case, the background, so the snow, is in this case is the one that actually well, is the feature that is one of the most important. And this is not how we as humans want to do that, or want recognize, distinguish between these two animals. So that's also the wrong way how we build the model. So this is not how we should do that. And actually explaining it, we understand that actually even achieving a high accuracy, it might be that the model is just not developed in a proper way. Or here another example, where I have a Tesla car that drive into the track. Or here another case of the tweetbot by what that was developed in 2016 by Microsoft. Actually, in this case, it was more actually related to the security part of the model. That actually it wasn't really well secured. I mean, the feeding and retraining it. But anyway, we also want to understand how it works and why it is actually trained in this way. So that's important. Or here with the adversarial attacks and the sticky notes on the signs, for example. Or here an example of Alexa suggesting to suicide yourself for a better good, which is obviously not the way how we think Alexa should work. And we want to understand why actually Alexa suggested such a thing. Explain that, right, to avoid this kind of situations in the future. Or another one, this one by Google, right? That's another one actually, a racist one, just by training with the wrong data set. So when it comes to explainability, we have different kind of methods. We have the black box methods, similar to actually testing. I mean, software testing. We have the black box and white box methods, and similar to the software testing, we have the black box methods are the one that actually doesn't know what's actually inside, and the white box methods, we know exactly the model, so we can easily explain what's going on. So one of an example of a white box model is actually our decision trees. So decision trees by design are explainable, because we can easily convert our decision tree to a set, let's say, to switch cases or if statements, and that's quite easy. Well, some people also think or say that actually it depends also on the complexity of the tree, and I agree that if the tree is just too complex, and especially if we use an ensemble method like, I don't know, random forest or XGBoost, so still we have decision trees in the back, but it might be that it's just too complex to understand that. But by design, decision trees are explainable, similar to linear regression, which is one of the, well, some people that say that it's not even a machine learning method, it's more a statistical method, but let's agree it is. So linear regression is easy to understand, easy to plot. Sure, if you have more features, it's not possible to plot, right? Like here, 2 dimensions, 3 dimensions, maybe 4 or 5 is possible. But the more features we have, it's more complex to draw it. But still, it is explainable. Right, decision trees that I mentioned. So let me show you an example here. So I will switch to my notebook. You can also find it on the on my GitHub account. So what's the difference between a black box and a white box? This is what you can see here. I will just make it bigger. Here we go. So here, what you can see is just a neural network with 3 layers, right? You can see the 3 layers here. So simple, not very complex neural network that where actually I use Keras to build such a network and we do a prediction, a classification in this data set. You can see the training we obtained, well, quite a impressive accuracy, like 90-80%. Good. But let's take a look. What's in it? What's in the network? So if you get the weights from the second layer, right, we will get something like that. So many weights, and obviously it's not possible to pick just one of these weights and say, oh, this number is responsible for this or that, because there are so many weights. It's not really possible. I mean, in this case, even such a simple network is not directly explainable just by design. So if we compare it, for example, to a decision tree, here's our decision tree based on scikit-learn. You can see that even if you don't know actually here what's the Gini index here, right? Or because Gini is one of the methods actually that allows you to divide, to split the nodes into subnodes, the child nodes, then still you can easily figure out, oh, okay, if it's below, or if it's true or false, then I can actually I can divide, I can split. So you can easily do a if statement. This is obviously a binary one. The decision trees actually are not binary, more complex, but still you can do several if statements to actually explain that. So this is actually the main difference. So let me just go back to the slides. Here we go. So another thing, there are also some insight, let's say, that should be given when it comes to the 3 questions related to the explainability. So first of all, something that I said before already. So what are the features that are really important? What are the most important? If you see the decision tree, you can easily, because the decision tree additionally is a method that actually can allow you to figure out the importance of features. Because if you have let's say 5 features and only 3 are used for doing the splits, in general on the whole tree, then obviously you just need only the 3. You can skip the rest one because the rest doesn't have any influence to the final prediction, right? So what kind of features actually really affect, right, the decision or the particular the prediction, right? And at the end, how each feature affects the model's predictions in a bigger picture. So going back, we can actually, using actually explainability, we can do some debugging, some by the data scientists, so understand why actually decisions are made, and then try to change that if it's not the right way. How, like the example with the wolves and the husky dogs, right? We can also, because sometimes it's not about the model, but sometimes it's actually related to the data, right? And actually, in many cases, maybe not most, but many cases, it is actually related to data. So sometimes it's more about improving the process, actually getting the features, right? Or actually collecting the data, right? Also, you saw also the racist one, right? The image that I showed you. So the bias removal, right? So feeding the right data, that's also part. And at the end, if the method if the model is actually prepared properly, then we also build trust that we know that actually is right, that it's doing the right thing, by also explaining to the humans with, for example, an if statement, right? And at the end, or analytic overfitting, but that's something that is actually quite obvious. So when it comes to debugging, some data leaks in general, leaks that we can find some underfitting, overfitting parts that we can see also here. I mean, it's not that we need explainability to find underfitting, overfitting. It's quite easy actually by dividing, for example, the data set into different kind of ratios, like training, testing data sets, and actually finding here when actually it's growing, and then it actually it stops to grow, and it might be that here is actually the point where actually it's overfitting, and obviously our underfitting, we see it by the accuracy at the end. So improving the feature engineers, maybe creating some new ones. Like I have here in the Titanic the demo. You can also find it on my GitHub. It's a bit more complex, so we don't have enough time to explain that, but you can find the Titanic data set where actually we add some new features to find more, well, to explain better, or explain better the model, and then also get higher accuracy, better prediction at the end. So again, how we should collect the data, maybe adding some new sources, not only maybe table data, maybe some images, maybe some maybe also some signals, right, sounds and so on. That's something that we might add, and maybe it can change the accuracy, make it more well, just better, right? Obviously human decisions, building trust, and removing the bias, right? So the black box method is, oh, sorry for the header. It should be, instead of white box, should be black box. So the black box method are the ones that we don't understand. I mean, we see the model, we understand the architecture, but we don't understand, or we don't understand what actually inside, why the weights are set in this way. And a good example of such methods is a group of methods actually are neural networks, as I showed you before, right? If we have some layers, it's hard to find out which weight actually means something, or maybe there's a group of weights that mean something. All right, models that are easy to explain. Non-linear regression, for example, k-means, so any kind of clustering methods, or most of the clustering are quite easy to explain. Decision trees, again, because at the end you can also do something like that. Instead of a tree, you can just split the feature space into just small spots, and actually try to, let's say, have as part of the image, part of the feature space that actually we actually have only objects of specific class. Or maybe this one might be a surprise for you, but also support vector machine. Even it's quite complex method, because in the background you use the Lagrangian multipliers to calculate that, and you can actually go to infinite dimensionality of the feature space. Still, that's explainable, because you have quite a easy to understand and explainable hyperplane. Also the margins. That's well, that's doable, definitely. Reinforcement learning, that's also something that is explainable, because we have the rewards. We have we know where actually we go in the next step. So we have also the matrices, where actually we have the steps from which we can go to another one. So it's quite easy to understand and explain. So I have another one. Here we go. So shallow methods that we can explain. You can go through here, through the whole through the whole notebook. But it's, it is explainable, like here, the linear regression, right? Even if it's not explainable in 2 dimensions, you can still explain it in more dimensions, right? Because it's not just in one, like here, right? So then you can plot the hyperplane, and even linear regression in a higher dimension can be explained with such an image, which is quite easy to understand, having this one, right? And the data explained additionally. Or you can also go for logistic regression that I showed you before. If it's not explainable in 2 dimensions, just move it to a 3 dimension, and it's more easier to actually do that, right? Like here, you can see. Or actually SVM, right? Like here, you can easily do that. Here's an example of fraud detection using SVM, and it is definitely explainable. Just a few examples more. We don't have enough time to actually go through each notebook, but I would like to leave it with you after the presentation, so you can go into details and go through each of these to understand each of the model in more details. So we have also models agnostic methods. So methods, not machine learning methods, but methods to explain the machine learning models. And we have 3 types. So we have based on the feature influence. So what feature influence the output mostly, or actually can be explained, let's say. Second, we have the output explanation. So we say, okay, that's usually I would take by example, like explain what's the output of that and why is like that. So we explain, rather than the whole model, actually what's going out of it. And the third group is actually the one of methods that are related to neural networks, right? To try to extract, for example, one layer and try to explain that. So we have plenty of different kind of methods for, I mean, the agnostic methods, right? So it doesn't matter what kind of model we have, or in most cases, it doesn't matter what kind of models one we have in the back. We can still use these kind of methods, and there are some of these here mentioned. So the first one with the influence method, the second with not feature but the output methods. Another typo, so we have Lime. Well, most of the methods, you can find libraries in Python that can be used to just directly to your scikit-learn or to Keras. I mean, maybe not Keras. I mean, Keras, yes, you have another one, other group of methods, but in this case, you have methods that are actually related to, for example, to scikit-learn just directly, and that's easy to use. So you can start right away, right? Also a few more one. Here you can see actually there is a source here on the bottom of my slide. That's a really nice book that actually some of the examples are taken from this book, a good one on explainability. I'm just writing my own one, but it still will take some time to finish it. Actually, I focus on the medicine, so I have specific applications that I want, that I actually, well, actually I use the methods. And here, as you can see, some influence of specific features. You have temperature, humidity, and wind speed, and how actually it affects the sales, right? Here we go. The advantage, clear, easy to interpret, right? Limited amount of number of features. That's actually one of the drawbacks. ICE, similar, but in this case we take more examples, right? More examples to that, and based on that we see actually where actually it is, where you have the more, let's say, black parts of the charts where actually we should focus on. It's also intuitive to understand, so easy to understand. On one hand, just one feature can be displayed on one chart because of so many of these, right? So compared to this one, actually you can put it on one chart here as well, just with, for example, with different color. So we have ale, which is another one. We just take the local effects, and again, it's easy, as most of the explainable methods are easy to understand. Compared to the ones, it's faster to compute because they are just taking less resources. In many cases, they give more information, right? But we have also the intervals, like as you can see here, that makes it maybe not so good when it comes to readable, give potentially less information. Depends obviously on the case that you have. So we have the Lime. That's a very popular method, that the local surrogate method that we can use. Plenty, I mean, not maybe plenty, but just, these are few libraries that are ready to use. So what we do, we try to explain part of it and actually try to distinguish and try to find out, okay, this part is actually of this group or this class, the other one on the other side is this group. So we try to make this kind of a hyperplanes here. Easy to use, explanation are quite short, right? On the other hand, well, we need to prepare the data properly, right? The scoped rules are similar to that. We just create, instead of that, we create just a subset, right? So a bit different to Lime. Chapel values, where we again take the features, like you can see here. In this case, actually, this is a real estate example, where actually it's based on the game theory. So we do the prediction, or treat the prediction as a game. But on the other hand, it's quite complex because if there are more features we have, it's much more complex. So it's not so easy to compute. SHAP. So as you can see, we just take part of it, right, and try to focus on that. That it makes the most important. That makes the prediction. What made a pixel that make them has the most influence, right? Quite easy for trade. I mean, fast for trees. It's actually a combination of Lime and the Shapley values, right? So that's probably the name comes from. And yeah, that's that. So deep learning methods, that's a bit more complex part because, as you know, I mean, You can do adversarial attacks on any kind of model, but the deep neural networks are specifically, let's say, they are complex. So it means it's not so easy to find and actually avoid this kind of attacks, right? As you can see here, you can do it on avatar cars, on different ones, but especially actually the neural network became more and more, on one hand, more precise, because I can see the new networks are more accurate that are proposed, and that's good because we are going in a good direction. More different kind of the networks are presented. Here, an example of an exception network. You can see it's quite deep because each of these blocks represent a separate layer, like this one, for example. But on the other hand, the bigger the network is, I mean, the more parameters, the more ways you need to set, doesn't always mean it's better. As you can see here, that if the bulb is bigger, like the VGG16, for example, compared to Inception version 3 here, there's a huge difference in the number of parameters that you need to set. But on the other hand, the Inception is give better results. In general, obviously, this is actually used on ImageNet, so just to have a similar data set to compare. And not always more parameters, more layers like here means better, right? So how to explain our neural network? Quite easy. I mean, easy. You have one of the methods that's easy to use as spatial images. This is the class activation map. So I can show it here in the notebook. If you want to, I'll obviously learn more about it. You can find it on my GitHub. In this case, I used a convolutional neural network. It's not so deep, really. I mean, it's VGG16. Okay, in this case, so it is deep. So maybe, I mean, we have many layers. Let me just make it bigger. And yeah, you have here, it's the way you use the weights from the ImageNet, and also use some images like the dog, for example, to predict. And yeah, it's a golden retriever. So we can tell, if you know what kind of dogs we have, so you can for sure say it's a golden retriever. That's true. So we have a good prediction. Cool. But on the other hand, why this method, this model, predicted that it's actually a golden retriever, right? You can see also the prediction. So we have 3 different kind of dogs. So there's a huge difference between the other ones. So the complexity you can see of the model is well, it's quite huge or quite big. And if you take one of the layers, in this case it's the last convolution layer that's usually done, so this one, you can prepare a heat map. So which part of the image actually was taken as the most important one to actually get the prediction. So you can build a class activation map, and actually if you combine it with the original image, you can see, oh, okay, makes sense. Makes sense. Most of the actually here, these colors make sense. Like, you know, the chest, the ears, the eye, and so on. So this is actually most important here. Also the back here of the dog. That's the most important pixels to take the decision that actually it is this is a golden retriever. Also the colors that are here included, right? To also take important part of the prediction. And then you can take, you know, as an example, you can see a cat here or a different dog, the Maltesian dog, much smaller one. You can see also that, okay, the chest, the ears, the eyes, yeah, are taken into account. So that makes a lot of sense. And actually, if you think about deep neural networks and the FDA for the medical applications, these ones actually are fine. I mean, they got an approval. They will get an approval if you build a neural network based on a convolution network or some convolution layers that I can explain, especially if you use images. I know at least a few examples where actually the companies obtained FDA approval for such matter. So here in summary, but still, what actually is important, just going back to the topic that I mentioned before about the deep neural networks, to explain that, well, because let's take this example. We have 2 images, two pandas, right? At least most of you will tell, okay, there is a panda on both images. But actually, it is one is actually panda, and the second is a gibbon. I mean, by the net, this is a prediction by of a neural network based on the images, the one that I actually showed you just before. And obviously, the second one is not a gibbon, right? It's not a type of a monkey. This is still a panda, but we can change the image, just changing a few pixels that for humans are not readable, but still, but the neural network will take these pixels into account and actually will see a gibbon instead of panda here, right? Or given a noise like here, right? That is not visible for us, but it's visible for the neural network. Or here, if you have more examples, like with a targeted and untargeted attack. In this case, we have the 1 pixel change. You can see 1 pixel here, and the cup will change. It will change from a cup to a Zippo, or from a bassinet to a paper towel, for example, or if a hamster to a nipple. That's not the. I mean, that's an easy way. Obviously, if you know where to put the pixel on the image, add the pixel on the image to fool the neural network, and this is actually where neural network the explainability makes even more sense to find out how to actually avoid this kind of attacks. So here I have more examples of such. Well, with the black box actually attacks. In this case, we have here you have, for example, the let's say dog sleep, right, and it's changing to this one. Right, so that's weird. Or here another example of a patch. Here the person is recognized as person. On the right, because of the image here, it's not recognized as person. I guess you can also find on Amazon or similar ones the T-shirts with this image that just not be recognized by human as a person by the neural network. Yeah. So just a summary. Please use explainability. Try to go deeper into it, especially if you're in the medical and finance industry, where actually it is, well, it's not, there is no choice really, right? You need to do that, but please go into it just to understand the models you build, why you build, how you build, and what are the results. If you want to learn more about actually, commercializing this kind of models, you can find also on YouTube one of my TEDx talk about how to apply, how to actually build models for the medical devices, for the medical industry, how to move it from the science, let's say, scientific idea to a commercial product. Yeah, that's all from my side. I hope you enjoy it, and maybe there are some questions.
Thank you very much, Karol. Actually, you've done such a good job of explaining explainable AI that we haven't had any questions yet. But if we do have some, please, would people like to enter them in the chat? But whilst they do, I have a couple of questions for you. So,
Sure.
And I'm going to declare right now that as a data scientist and a behaviorist, I'm using AI to understand emotions within narratives and the role that they play in decision making. And boy, is that difficult. Anyway, this is my first question. So I'll start with a statement. I mean, if you're in business today, you're in the business of data and increasingly in using artificial intelligence. But many leaders still have unrealistic expectations about what AI can and cannot do. So what would be your tips to explain to the lay person, somebody who doesn't have the time to understand the data science, the limitations of AI? And I'm not talking about generalized AI, although I think people still think that's a thing. But how can we explain to business users, for example, what AI can and cannot do?
Well, because I'm actually 15 years in the industry, and I do machine learning for so many years. I see how it changed. At the beginning, the companies were rather, oh, we don't want to use machine learning. We don't see a business here. Now it's actually totally opposite. And I train people how not to use in many cases actually, train people how not to use machine learning instead of how to use machine learning, because now everyone wanted to use that. And the thing is that machine learning is not a solution for everything. there are simpler methods to solve that. And what I would like to recommend, please first check if you want if you want to apply, for example, a natural language processing model, maybe a regular expression is good enough. It's cheaper, faster, makes sense, right? And solve the problem instead of building a complex model that might not give you the results that you're expecting. So find simpler solutions and fail fast, because this is still research. So please don't invest a lot of money if after a few weeks it doesn't work. Maybe it's not doable. Maybe it's not something that can be done. And please do due diligence before you try to solve the problem. Please do due diligence, because that's crucial. You can explain if it's really doable and if it makes for sense for the company, because sometimes it's cool, it looks pretty and very, very interesting, but at the end it will not get any kind of I don't know, increase or decrease in cost for the company. So maybe it doesn't make any sense.
Great. Thank you very much, Karol. I do sometimes feel like we're living in a Dilbert cartoon when it comes to AI, and that the CEO is saying, go and get some of that AI stuff. It'll be brilliant and transform our business. Now, we have had a couple of questions. So the first of which is, where can people get the slides? And I think you had your contact details, didn't you, on the slides? Let me just put that back up for a moment if people want to get hold of you. So hopefully they can see that. But what I would also like to do is ask the second question, and this is a good one as well. Is it sometimes worthwhile to sacrifice model accuracy for the sake of explainability? And in here, it's, for example, in the domain of medicine. So is it sometimes preferable to sacrifice a bit of model accuracy in order to make it more explainable?
Well, I think it depends. If it's scientific, for example, for a paper, then obviously just leave the accuracy high. But if you want to commercialize that, well, there is no choice really, because you need to explain it to get it to the market. So you need to find out how not to get the accuracy decrease. But please keep in mind that accuracy is not the only quality metrics. I mean, even more, I think accuracy is one of the worst quality metrics that should take into account. There are other ones like specificity, sensitivity, F1 score, and so on, that you should think about more rather than actually accuracy. I know accuracy is easy to explain, but for example, for the doctors, it's important that actually the model will actually find the cancer more precise than actually. It's better to find it more precise to find cancer rather than tell more than it's not a cancer, right? Because if you tell it's not a cancer but actually it is, then obviously for this person it's not again good information. So even if you go down with accuracy, but you are able to explain that, and the metrics are still, let's say, stable, especially the one that actually affect the human more, then this is well, you can sacrifice, let's say, the accuracy of such model.
Yeah, thank you very much, Karol. Yes, the case you've raised there is a great one, in that it's more important that we find the cancer, even if it means accepting we will get false negatives, so that we do actually catch more of the cases rather than have a completely accurate model, which is 100% accurate at finding it, but misses cases. So I think that is a balance that we all need to strike. Finally, that question about the slides, if you've got a paid ticket, you will get access to the recordings afterwards. Anyway, that unfortunately brings us to the end of the time for this session. So all that really remains is to thank you, Karol, for a great presentation. I learned lots, way more than I actually know how to use, but I think that's a good thing. So thank you very much for that. And until the next time we get a chance to talk, take care and goodbye. Cheerio now. Bye-bye.
Thank you. Bye-bye.